All right, our last section. So this is 9.4. Yes, we skipped 9.3. So 9.4 is counting techniques and probability. Okay, so remember last time we talked about our fundamental counting principle. So really they're a little behind in their ordering of these sections, but we'll work with it. But we already briefly know what it meant to be our fundamental counting principle. You can read this if you want to, but it's another one of those real wordy definitions. So we're just going to refresh our memory with, let's say, we had 3 shirts, 2 pair of pants, right, and 2 shoes. Maybe I can make this fit on here. And we want to know how many outfits we could form. We could go back to our tree diagram, right? Let's see, this is our shirts, right? And I have a red shirt, a blue shirt, a yellow shirt. And then if I had 2 pair of pants, let's say I have jeans and khakis. With each one of these, I have jeans and khakis, right? Jeans and khakis, jeans and khakis, and 2 pair of shoes. Let's say I have sandals and tennis shoes for each one of these. Sandals and tennis shoes. Okay, sandals and tennis shoes. Then the tree diagram tells us how many possible outfits we have. We could have a red shirt with jeans and sandals, a red shirt with jeans and tennis shoes, right? Following each path. We've already done this. A red shirt with khakis and sandals, a red shirt with khakis and tennis shoes, a blue shirt with jeans and sandals, a blue shirt with jeans and tennis shoes, a blue shirt with khakis and sandals, a blue shirt with khakis and tennis shoes, a yellow shirt with jeans and sandals, a yellow shirt with jeans and tennis shoes, a yellow shirt with khakis and sandals, a yellow shirt with khakis and tennis shoes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have 12 possible outfits, right? 12 possible outfits. The great thing about the tree diagram is that it tells us what every one of those outfits are. So then I could ask various questions about particular outfits. But if my question was just how many outfits do I have, this fundamental counting principle tells us that all we have to do is multiply my options together. So since I have shirts, pants, and shoes, right? 3 branches, 3 items, 3 spaces. I can just fill in my options in each space, and the fundamental counting principle tells me to multiply. 3 times 2 is 6 times 2. Voila. Okay, so that's our fundamental counting principle that really we've already discovered, but we're just now kind of clarifying. Okay, fundamental counting principle tells you multiply. Okay, remember when we talked about the dice last time? When you're rolling 2 dice, there's not 12 possible outcomes, but 36 because it's 6 times 6. Okay, so now that in conjunction with a couple of other counting ideas, the first one being permutations. Okay, so permutations is an arrangement of things in a definite order with no repetitions, this says. right? An arrangement of things in a definite order with no repetitions. For example, what if we wanted to know how many different lines we could make? There's 9 of us in the class, right? And how many ways could we line up? So key words that we're looking for, it's not always in there, but if I see the word arrangement or a lineup, I'm thinking about permutations. So if I know there's 9 of us in the class, that's 9 spaces that can be filled. Okay, so to fill in the first space, any one of you guys could get there, right? Elizabeth, Vera, John, Dylan, anybody could be here. But once one of you stands there, then there's only 8 people that could get in the next spot. And once someone is in that spot, there's only 7 people left that could get in this spot. And it goes down like this all the way to 1. Okay, so that's how many different permutations, arrangements can be made if we line up 9 people, right? How many different lines can be formed? Because it's a different line if Luz is in the front or if Luz is in the back, right? Those are 2 different lines. Now, if we have something that goes down by 1 and is multiplied and goes all the way to 1, we've got a shortcut for that. I could type this in my calculator, 9 times 8 times 7 times 6. What if there were 24 of us in this class? Do we really want to type in 24 times 23 times 22, ... So we have a shortcut for that. It's called a factorial. And the mathematical symbol for a factorial is an exclamation mark. So what this is saying, there's a, by the way, I don't know, oh, that's a K, this should be ... Right? So in our problem up here, 9 factorial means this, right? You start with 9 and you subtract 1 every single time and go all the way down to 1. All right, so we don't have to continue typing that in our calculator. Look for your key. Some of you might see this or just this on one of your buttons right on the front of your calculator. If you don't, some of us are going to have to go into the math menu and then from there the probability menu. Now it might have PROB or just PRB, and some of you will have the probability button, PROB, or just PRB as one of your buttons. In my graphing calculator, I have to hit math, and then across the top, there's a PRB. I can go over there, and then if I look down at the 4th one, I see an exclamation. All right, so if you can't find this factorial button on your calculator, be sure and call me and we'll help you go through the process on your calculator. So what you'll do is you'll hit the number 9 and then you'll go in to wherever you have that factorial. You'll hit it. It'll enter this then on your calculator. You hit equal and it will tell you that that is 362,880 different lines that we could form with 9 people. Okay, so that's a permutation. Okay, what if I wanted to know how many lines we could form if just 3 of us were lining up? Okay, so then if I just want to know about a line that's 3 people long, there's only 3 blanks to fill in. Okay, there's still 9 of us that could get in this first spot. Any one of us could stand right here, right? But then once Caitlin or Laura or Emma or whoever it is that's standing right here is standing here, then there's only 8 choices left, and then there's only 7 that could get in that 3rd spot. Now on one like this that doesn't go all the way to 1, I can't use my factorial button. So I'm just going to have to type in that 9 times 8 times 7 in my calculator, right? And see that that's 504 different lines that we could get that's 3 people long instead of all 9 people long. Okay, so additionally, we have a formula in our calculator again for that. If it's a permutation, I'm not ever going to use this formula. I'm going to fill in the blanks. But I want you to know where the formula is. So you're looking for something that looks like this, right, in your calculator. And once again, if it's not on a direct key, look in your probability or your math. If you had to go into one of those different menus to find your factorial, you probably saw this symbol in there. So where this is useful, now I'm going to use the factorial if I'm just talking about arranging all 9 people. But what if we said, well, there's 9 people that we're going to use to arrange, but I only want the line to be 3 people long. That's where this R comes from. So this then becomes this. It's 9 permutations taken 3 at a time is the way you would read that. Okay, so N, and if you get these backwards, your calculator will give you an error, so you'll know. But the big one has to come first. So there's 9 people to select from, but you only want to line 3 of them up. So you go on your calculator, you hit the 9, you go into wherever you have found this symbol, and then you hit the 3, okay, and you hit equal. That tells you 504. Okay, notice the exact same thing we got when we did this. Okay, so I've got the n factorial. This was the 9 times 8 times 7 times 6 times 5. N minus r in this case, so in this case, this formula, if we worked it out, would look like this. Right? N minus r, 9 minus 3. And notice if I did times 6, 5, 4, 3, 2, 1, and then divided it, 6, 5, 4, 3, 2, 1, that's why the technical formula has this in the bottom. I'm always going to fill in the blanks. Okay, because I'm going to have another place in just a moment that's a combination. So you might in your calculator right now, wherever you're seeing this, right beside it, you're going to see the one that looks just like this except with a C. Okay, so I got to pay attention to the difference between a permutation or a combination. I'm going to use the formula for the combination because it's a little more complicated than this. But if it's a permutation, I'm going to use the lineup. Mainly because I can also use the lineup with my fundamental counting principle. Let's say that we still have 9 people we're trying to line up, but 5 of them are men and 4 of them are women. And I want to know, well, how many lines can we make if we start with a man first and then we alternate by gender, right? So there's still 9 people that I'm going to line up, but I can't use either one of these formulas. Technically, this is a fundamental counting principle formula. It's not a permutation, it's not a combination, but those fundamental counting principle ones, I can think of as permutations because they work exactly the same way, except I can't use my formula on them. So I'm never going to use this formula. Since I can't always use it, I'm never going to use it. Okay, so in this case, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, if we've got 5 men, then there's any one of 5 people could go right here. Okay, and then the next one has to be a woman. And I said, okay, so there's 4 women, so any one of the 4 women could go here. Next one has to be a man. So since 1 man is standing here, there's only 4 left that could stand here. Okay, now I've got to have a woman, but 1 woman is standing here, so there's only 3 left. Okay, now I've got to have a man, but there's a man here and a man here, so now there's only 3 men left. Okay, now it's got to be a woman, but because there's a woman here and a woman here, there's only 2 women left. Now there's only 2 men left, and now the last woman and the last man. Okay, so I would just have to punch this in my calculator. 5 times 4 times 4 times 3 times 3 times 2. It's not a permutation. Can't use my formula, but I can use the same process. Just like that first question where we said, how many outfits can we make? That's not a permutation. But if I'm trying to count how many different, pieces of clothing I can line up to form an outfit, I had, what did I say, 3 shirts, 2 pair of pants, and 2 shoes, right? So if I decide it's a permutation or not a combination, I'm going to be filling in the blanks. You do have the option of this formula if you so choose. Okay. A baseball team has 9 players. Find the number of ways the manager can arrange the batting order. Okay, basically, I didn't catch the fact that we have 9 students in it. So this is the same problem. If there's 9 players that I need to line up, right, to go in some kind of order to get up and bat, I'm filling in 9 blanks. Any one of the players could go first, but once one has batted, there's only 8 left that could go next. So if we go all the way to 1, then my shortcut is that's 9 factorial, and we just did that. Let's see if it's still on my calculator screen. Yeah, 362,880. Okay, what about this one? Find the number of ways of choosing 3 initials from the alphabet if none of the letters can be repeated. Okay, so 3 initials, that's 3 blanks I'm going to fill in. If none of the letters can be repeated, then I've got 20, how many letters are in the alphabet? 26 letters in the alphabet to choose from first, anything from A to Z. But then once I've used one of the letters, since I can't repeat them, there's 25 left. And then once I've used 2 of the letters, there's 24 left. So if I put that in my calculator, I have 26 times 25 times 24, or 15,600 different sets of initials with 3 different letters. Likewise, for those of you that want the formula, you could have plugged this in your calculator, right, and gotten the same answer. 26 permutations taken 3 at a time. But what if this didn't say this last part? If the letters can't be repeated, then it's still filling in the 3 blanks. I still need 3 initials, but 26 times 26 times 26, it's not a permutation technically. I can't use this formula, but I can still fill in the blanks. So now I could have an AAA initial, right? Or ABB initials. They could be repeated. 17,576. All right, so basically for permutations, this is the last time I'm going to reference personally the formula, but if you prefer, you can continue thinking of it that way. Okay, now what about permutations involving like items? Okay, so again, you can read the wording here, and again, this should be dot, 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 all right? I don't know why K is dot, dot, dot. Okay, but what it is saying is, if you have items that are alike, for example, let's just take the word box. And if I want to know how many different ways I can arrange these letters to form a different, you can't see me, but I'm making air quotes, word, right? It doesn't have to actually be an English word, but just a different arrangement of the letters. I could trade places with those too, right? And then I could put the O first and a BX, the O first and an XB. Okay, or I could put the X first and a BO, or an X first and an OB. 1, 2, 3, 4, 5, 6. Notice if I have 3 letters, that's 3 spaces that can be filled in, and I want to know how many different arrangements I have. Well, I could choose from a B, an O, or an X to put right here. But once I've put one of them there, then I only have 2 choices left. Oh, yeah, 6, which I can see right here. And here's the 6. But suppose my word instead of box was Bob. So I could trade places with that B and O, so there's 2. But now if I put the O first, right, and then the first B and the last B, and then I trade places with these, so that's the last B and the first B. These aren't really different arrangements, right? So that's what this means. It's still different arrangements, but if any of them are alike, I'm not going to have as many different arrangements as if when they're all different. So that's why we divide some of them out that's the same. Okay, so what this formula really means is, for this example, however many letters or whatever it is you have that you're trying to arrange, in this case they're letters, we put here, and then all of this is how many you have that's alike. So for example, if I have 2 of them that's alike, okay, and then one that's different. Now a key for me is that these 2 numbers need to add up to be this number. That's how I know that I'm good, right? Okay, and 1 factorial, that's just 1, right? Because it goes all the way to 1, so that's just 1. So really we can discard that. So this is 3 times 2 times 1 over 2 times 1, technically times 1. Or notice, oh, we only get 3 different arrangements, right? And here they are, 1, 2, 3. Okay, so that's a formula that I want to be aware of and add to my list. Permutations of like items. So for example, this says find the number of rearrangements of the letters in each of the following words. Well, if I notice that some of them are the same, I got to say, oh, that's that special formula. I'm still arranging, so it's a permutation, but if any of them are alike, here's how I do it. 1, 2, 3, 4, 5, 6. So I have 6 factorial on the top. Now there's 3 B's. There's only 1 U, 1 L, and 1 E. Double check myself. 3, 4, 5, 6. Check. Okay. But then I can also realize that all of that's just 1. So I have 6. Now look at a shortcut I can do. 6. Yes, I could go in and put this on my calculator also and put 6 factorial divided by 3 factorial. That's fine. But that's so many keystrokes that it's kind of nice to know the shortcut here. So technically, here's what I have. 6 times 5 times 4. And look what I can do. I can just make that 3 factorial. Because this is 3 times 2 times 1. And this is 3 times 2 times 1. So really on my calculator, all I need to do is 6 times 5 times 4. Or maybe I can see that this is 6 times 20. I don't even have to pull out my calculator, much less punch a ton of buttons. All right, let's try that again. Oh, as soon as I notice some of the items are alike, then I've got a formula for that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is 10 factorial over, there's 3 S's, 3 T's, 1 A, 2 I's, and 1 C. 3, 6, 7, 8, 9, 10. Perfect. I feel comfortable with that. These are just 1. So I can say, well, hey, this is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 factorial. Go to whatever your biggest one is. And then I have a 3 factorial. Once again, you can plug this in your calculator. I know some of y'all are just going to say, let me plug it in my calculator. All right, so I've taken care of this one. Now the next one is 3 times 2 times 1, and the 2 factorial is 2 times 1. So this will cancel, right? Oh, look, here's a 3 times 2. That'll cancel that. Okay, this 2 will cancel right there. So really all I have to enter in my calculator is 10 times 9 times 8 times 7 times 5 times 2. Some of us might notice, hey, this is 10 times 10. 100 times 9 times 8 times 7. Not 987, but forget your times in there. 9 times 8 times 7. So 50,400. Different ways to arrange those letters. If you're just going to use the factorial symbol in your calculator, don't forget you got to put parentheses around here, right? Because if not, once you divide by this, it's going to jump this up and make it a multiplication once you hit a times right there. So put parentheses so that it keeps everything in the denominator. Okay, but mainly I got to know this formula, right? And then we can just choose however we want to work it out. Okay, now to combinations. Okay, a combination, I don't like the way they use the word arrangement here. Really, you don't really ever see that in the definition of combinations. And when you're doing a combination, you don't talk about arrangements, right? So, but they're saying an arrangement of objects in which the order makes no difference. So here's the difference between a permutation and a combination. And here's the first question we got to ask ourselves when we're trying to count these things up. Is it a permutation or a combination? Or is it a combination or not, which means it's a fill in the blank. Okay, so remember when we were talking about permutations and I said, and then there's 9 of us. So I said, how many different lines 3 people long can we make? Okay, that's a permutation because the order matters, right? If Mary Lou's is here, that's a different arrangement than if she's over here, right? So any one of us 9 could go first, but then once one person's there, okay, so that's the permutation. Or I said I wasn't going to refer to this again, but here I go one more time. Or if we're using the formula, it's this. Now here's the difference. What if I said, how many different ways can I send 3 of you to the library? In that, let's say this is Chrissy, Luz, and Emma is one line, right? And Emma, Luz, and Chrissy is a different line. Chrissy, Emma, and Luz is a different line, right? Let's think of these as, first place, the first one that gets up there. It's different if Chrissy wins and she gets in the first place, or if she's third, right? It's different if Emma is first or second. So these are different lineups, different arrangements, right? I can just tell by looking at the letters, they're different arrangements. But if I just said, hey, I'm going to pick 3 of you to go to the library, and I tell Luz, Emma, and Chrissy, go to the library, it doesn't really matter if I say, hey, Chrissy, Luz, Emma, go to the library. Or if I say, Emma, Luz, Chrissy, go to the library. Chrissy, Emma, Luz, go to the library. I've still picked the same 3. Those are still the one group of 3 that's going to the library. That's a combination. So it would still be, there's 9 of you I could have chosen to go to the library, but now we're going to use that combination one, right? And I've chosen 3. Technically, this is 9 combinations taken 3 at a time, but a nice shortcut is 9 choose 3. So just like the word arrangement or lineup isn't 100% definite that it's going to be a permutation, there are words like choose or select that the majority of the time, not 100%, but the majority of the time makes you think, oh, it's a combination, choose and select. So we can think of this as 9 choose 3. Now, if it's a permutation, I'm doing this. And if it's a combination, I'm doing this. And I think the next slide probably shows the formula for the combination if we want to see it. Oh, yeah, it sort of does, but they do it way crazy. Okay, technically this right here is your formula for combinations, right? So remember, for permutations, it was this n factorial over n minus r factorial. Now we're going to add in, we're going to divide by even more because, like I said, Emma, Chrissy, Luz is not a different group to go to the library than Luz, Emma, Chrissy, right? Okay, so the number will always be smaller. Okay, so in that case, here's what the formula would look like. A lot of times it's just simpler to see the numbers in there. You have 9 factorial, and you still have your 3 factorial, but 9 minus 3 is 6 factorial. All right, so it looks like this. If it's a permutation, it doesn't have this part. Combination does. You'll probably rarely, if ever in this class, later when you're actually working with this, you'll do this. But in this class, I don't believe there's ever any place where we can't just, use the formula from our calculator. If that's not true and we need help with this, let me know. Okay. So the Library of Science Book Club offers 3 free books from a list of 42. How many possible combinations are there? And look, this actually used the word combination, right? But what I need to think of is the order important? If it's not important, and think of this, your 3 free books. So if you choose, oh, I'm going to get 3 free books, oh my goodness, I choose to get Harry Potter, and then of course I'm going to get that math book, and then I'm going to get the Game of Thrones, right? It doesn't matter really which order I pick them. When they send them to me, right, there'll be those 3 books. That's what tells me the order is not important. I'm not arranging them on a shelf, right, and lining them up. I'm just picking them for them to send to me. So that means if there's 42 to choose from, and I'm going to choose 3. And I can just put that in my calculator. And get 11,480 different sets of 3 books out of the 42. At the beginning of the first semester of a mathematics class for elementary school teachers, each of the class's 25 students shook hands with each of the other students exactly once. How many handshakes took place? So they're still helping us think through what we need to know. Since the handshake between persons A and B is the same as that between persons B and A, right? This is involving combinations. The order that you shake hands really doesn't matter. So it's 25 people taken 2 at a time. I just have 25 people, and I'm going to choose 2 at a time to shake hands. So that's 300 different handshakes that are going to happen if everyone shakes each other's hands once. Given a class of 12 girls and 10 boys, answer each of the following. In how many ways can a committee of 5 that consists of 3 girls and 2 boys be chosen? Okay, it's a committee, so the order doesn't matter, right? It's just like if I chose you to go to the library, oh, you guys are going to be on a committee to decide what our project is going to be or something. There's no ranking, right? So if it's just a committee, it's a combination. But here, I've got 2 different things being asked. I want to choose a certain number of girls, and remember from our probabilities, and is a multiply, and our fundamental counting principle tells us to multiply. So I'm going to find how many ways you can get 3 girls and how many ways you can get 2 boys and multiply them together. So if there's 12 girls, I'm going to choose 3 of them. That's how many ways you can get 3 girls out of these 12. If there's 10 boys, I'm going to choose 2 of those. This is the number of ways you can get 2 boys from the 10. This is the number of ways you can get 3 girls from the 2. So all together, I multiply these 2 numbers to see what that is. And I can do it completely in my calculator. I can do it just like this. 12, choose 3, and then put the times. 10, choose 2 in my calculator. All right, so I've got 12. Choose 3 times 10. Choose 2. And that gives me 9,900 different committees that you can form if they consist of 5 people, 3 of which are girls and 2 are boys. Now look at this one. What's the probability? Oh, so now we're putting all of this together. The counting, remember when we're doing probabilities, you know, the probability of our event, we simply count the number of ways our event can happen over the number of ways the sample space can happen. In other words, any possibility, right? So if I want to know what's the probability, it's going to be a fraction. Pay attention on the test and on your homework. Is it asking how many, where you're going to have a large number, or what's the probability, where you're going to have a fraction, right? Probabilities are between 0 and 1. So what's the probability that a committee of 5, chosen at random from the class, consists of 3 girls and 2 boys? Oh, well, I already found out this number in the previous problem, right? So I know that's 9,900 because I did it in a previous problem. And now I just need to know, oh, how many ways can you choose 5 people, period, without any restrictions out of 22? Right? So that's how I find my bottom number, the total possibilities of getting 5 people out of this group of 22. So now if I do 22 choose 5, I see that that is 26,334. And letting my calculator simplify that for me, 50 over 103. So the only reason I did it like this is because really we had already calculated this number. I could have put this in my numerator and this in my denominator and done it all in one step. Or I could have found the number for the numerator and the denominator independently. Okay, what's the probability that a committee of 5, so we're still doing the same problem. So just to verify, whoops, we had 12 girls, 10 boys. Wrong way. 12 girls, 10 boys. 12 girls, 10 boys. Okay, what's the probability? So it's a probability that a committee of 5 chosen at random from the class have no boys. And the probability, your bottom number, is the total number of ways that you could get 5 from the total group of 22. Now, if I want there to be no boys, that means I'm going to choose the 5 people all from the girl slot. And out of the 10 boys, I'm not going to choose any. Right? So technically, this is what it looks like. Anytime we have a choose 0 here, and if I forget that, I can enter it in my calculator, and I could enter this entire thing. It doesn't matter. But it's a pain to enter these combinations and permutations from our calculator. Usually it's several punches. So anytime I have a choose 0, that's always 1. Right? That's always 1. So really all I have to enter in my calculator is 12 choose 5 divided by 22 choose 5. And I get 0.03. Now I'll probably need that as a fraction, so I'm going to go ahead and see if my calculator will turn it into a fraction. And I get 4 over 133. Okay, or I could have done this and gotten the number and this and gotten a number and then reduced it. Sometimes if your fraction is too small, your decimal is kind of oddball, your calculator has trouble turning it back into a fraction, so you could do it individually and get the numerator number and the denominator number. Okay, what's the probability that a committee of 5 chosen at random from the class consists of only girls? That's the same question, isn't it? No boys, only girls. We've already done that problem. Okay, just different ways it could be worded, but same process. Okay. Assume a class has 30 members. How many ways can a president, a vice president, and a secretary be selected? Is the order important? Yes, because it is different, right, if Vera is president and John is vice president than if John is president and Vera is vice president. That's a different order, right? They're ranked. So this is a permutation, and because there's 3 slots, right? But this time there's 30 members in this class, so any one of 30 can be selected to be president. But once you've selected one of them to be a president, he no longer can also be vice president. So there's only 29 people that could be vice president, and then once you've filled those 2 positions, there's only 28 people left that could hold the secretary position. 30 times 29 times 28. 24,360. Now this one, same thing, a class with 30 members. But how many committees of 3 people can be chosen? A committee has no ranking. right? You're all on the same level. So in this case, it doesn't matter if Elizabeth and Laura and Caitlin are on the committee, or if Caitlin and Elizabeth and Laura are on the committee. It's still the same committee of the same 3 people. So this time you've got 30 people and you're going to choose 3 of them. It's a combination. $4,060. Get the difference in the size of the numbers, because every single grouping doesn't count here, right? Okay, Sally has 4 red flags, 3 green flags, and 2 white flags. Each arrangement of flags is a different signal. How many 9 flag signals can she run up the flagpole? Notice they mentioned arrangement, but we've got some like items here. This is a permutation, but it's a permutation of like items. So let's say, 4 red flags. So 1, 2, 3, 4. Let's just say this is exactly what? 3 green flags. 1, 2, 3. And 2 white flags. I don't know if this will show up over here. It will not. Let's make them yellow instead of white. Barely shows up, so we'll imagine they're white. Okay, so our problem is, if I swap places with these 2 flags, it's not a different signal, right? If I swap places with these 2 flags, it's not a different signal. If I swap with these 2, it is, though. So I got to remember my formula. Now, there's 4, 5, 6, 7, 8, 9. So it's 9 factorial over, and because there's 4 the same, and then 3 green ones, and then 2 white ones, 4, 7, 8, 9, check. So I can come over here, and I can either enter all that in my calculator if I'm doing that, put parentheses, or I can say 9 times 8 times 7 times 6 times 5 times 4 factorial, because I've got one right there that'll cancel, but then times 3 times 2 times 1 times 2 times 1. So that'll cancel. This 6 will cancel, and I can take a 2 out of there. So what I really need to enter in my calculator is 9 times 4 times 7 times 5, or 36 times 35, right? 1,260. Or you could enter it like that. Okay, if you prefer this method but you're having a little bit of difficulty with it, and I would hope everyone would prefer this method, right? Just let me know. Shoot me an email. We can work on that. We can meet. Okay. How many arrangements can be made from the letters of the word friend? And it uses the word arrangements again, if all the letters are used. Right? So if all the letters are used, none of them are the same. And so because I'm arranging different letters, if I write ENDFRI, that's different, right? Even though it's the same letters, but it's a different arrangement. So there's, well, 1, 2, 3, 4, 5, 6. I've got 6 letters to choose from. Once I put one of the letters there, there's only 5 left I can choose from, and so on. So this is 6 factorial. So 6 factorial is 720. What if only 4 of the letters are used? Oh, that means I'm going to have a word 4 spaces long. There's still 6 letters I could put right there. And then once I use 1, 5, and then 4, and then 3, right? But now I can't use my factorial. I could use my other formula. Here I am doing it again when I said I wasn't. I could do that. I'm not going to, though. This is 20 times 18, so 360. Okay. I'm thinking that was the last one. And it was. Okay, so that's all of our content is finished. Okay, if you can get through all of this, let me know if you have any questions. And this is your last one. Okay, I'll talk to you guys later. Bye-bye.